In this module, we'll go over some basic math skills dealing with units, dimensional analysis, unit conversion, scientific notation, and significant figures. So let's start with units. We know that, for example, length can be measured in many different units like inches, feet, meters, miles, etc. Or as another example, time can be measured in seconds, minutes, hours, days, etc. We refer to general categories like length and time as dimensions. Other common dimensions are things like mass, speed, acceleration, force, area, and volume. And here are some common units for each of these dimensions. Most of these units you're familiar with, but there are some less common ones, like a slug, which is a unit of mass, or a dyne, which is a unit of force. Also notice that there are actually two applications for pounds, a mass pound and a force pound. Usually, when we say pounds, we're referring to mass pounds. Also notice that many units are combinations of other units. For example, a force pound is equivalent to a slug times a foot divided by a second squared, and a newton is equivalent to a kilogram times a meter divided by a second squared. Another key thing to know is that there are systems or groupings of units, such as the U.S. customary system, which includes feet, ounces, pounds, and others. The key system of units for our class, and many scientific disciplines as well, is the International System of Units, or SI. The SI units for the dimensions we have listed here are the first ones in each row. So listing them separately, we have this list of SI units. Make sure you know what the SI units are for each dimension. And since a newton is a kilogram meter per second squared, notice that all of these units consist of combinations of just meters, seconds, and kilograms. These are all then the fundamental or base SI units. There are a few other base units, but these are the main ones for our course. One thing I want to point out, because it's a common mistake, is that the SI unit for volume is meter cubed, not liters. The next topic, dimensional analysis, is related to dimensions in units. Dimensional analysis is a useful way to help ensure that you have written an equation correctly. Basically, dimensional analysis consists of two rules. One, when adding values, each value must be the same dimension and have the same units. And two, the final dimension and unit on each side of an equal sign must be the same. Here are a few examples. Is the following a valid equation? The answer is no, because these two terms in the equation do not have the same units. It doesn't make physical sense to add meters and kilograms. So here's another example. Is this equation valid dimensionally? Let's look at the dimensions of each term. The dimensions for an area are length squared, and the dimensions for r squared are also length squared. Pi is unitless, which means it's just a number without dimensions or units. So in the end, we have length squared is equal to length squared, which is dimensionally correct. And let's do one more. Is this equation valid dimensionally? The values check out. 3 squared is equal to 5 plus 2 times 2, or 9 is equal to 9. But let's look at the units, which simplifies to. And these two terms have the same units, so they're fine. But the third term is different because the meters are cubed instead of squared. So in the end, this equation is not valid. The next thing you must know in this course, which also relates to units, is how to do unit conversions. People use different techniques to do unit conversions. Here are a couple of examples showing a very popular and solid technique that I recommend. Convert 0.7 miles to meters. The basic technique here is to multiply by 1 in such a way that the units get canceled and replaced with the units that you want. Let's start by finding a conversion between miles and meters. You can find conversions like this in the textbook, or you might search for them on the internet. I do not expect you to memorize conversions like this, so they would be given to you on a test. A Google search tells us that 1 mile equals 1,609 meters. So now write down the original value, 0.7 miles, and multiply it by a ratio of 1 mile to 1,609 meters. This is where we're actually multiplying by 1. We set it up so that the miles get canceled and meters are left. And so multiplying it out, we get our answer that 0.7 miles equals 1,126 meters. Let's try another example. Convert 55 miles per hour to SI units. Again, we'll start by writing down the original value of 55 miles per hour, and I'll write miles per hour a little more explicitly so that we can do the process more easily. Before we start to convert these units, let's recognize what the equivalent SI units are for miles per hour. This is length per time, so the appropriate SI units are meters per second. Okay, with that in mind, let's do the conversion. Let's start by converting hours to seconds. You may not know how many seconds there are in an hour, but you know that there are 60 minutes in an hour. So let's start with that conversion. So that has converted hours to minutes. And we know that there are 60 seconds in a minute, so now we can convert the minutes to seconds. So we've converted hours to seconds. And now, by the way, we can see from the work here that there are 60 times 60, or 3,600 seconds in an hour, which is a useful conversion to know in our class. Now let's convert the miles to meters using the same conversion we used in the first example. And so we're left with meters and seconds as we wanted. And then multiply it out, and we get our final answer of 24.6 meters per second. I'll reiterate that for tests, you don't need to know conversions like miles to meters or mass pounds to kilograms, etc., but you do need to know metric prefixes, such as a milligram is equal to 10 to the negative 3 grams, or a kilogram is equal to 10 to the 3 or 1,000 grams. Basically, the prefixes to know are these: nano, micro, milli, centi, kilo, mega, and giga. And now the next thing I want to discuss is scientific notation. Scientific notation is a shorthand for writing out numbers with many decimal places. It's very convenient, and we will use it often in this class. Here's an example. 5,217 grams can be written as 5.217 times 10 to the 3 grams. And now in scientific notation, we simply replace 10 to the 3 with E3. Here I've used a lowercase e, but an uppercase E can also be used. In scientific notation, the base number is always written so that there is one non-zero digit to the left of the decimal. And then the E3 in this example represents that the number should be multiplied by 10 to the power of 3. By the way, per our previous discussion, 10 to the 3 can be replaced with kilo. So this number is also equal to 5.217 kilograms. Okay, here's another example. In scientific notation, the decimal must be to the right of the first non-zero digit. So the base number is 3.80. And that means that it has to be multiplied by 10 to the minus 3, or e negative 3, to move the decimal to the left 3 places. Again, just FYI, we can use a prefix, in this case milli, to replace 10 to the negative 3. This leads into another math skill that you need, and that's how to determine significant figures. Once a number is written in scientific notation, it's easy to determine the number of significant figures there are. In scientific notation, the number of significant figures, or sig figs, is the same as the number of digits in the base number. As an example, how many significant figures are there in this number? In scientific notation, the number becomes this, and we can see now that there are 3 digits in the base number, so there are 3 significant figures. Well, here's another example. This time there are 6 digits in scientific notation, so there are 6 sig figs. Or this example, the number is already written in scientific notation, and there are 4 digits, so there are 4 sig figs. Notice that the zeros to the right of the decimal are also significant digits, and so we had to count them. And now that brings us to the end of this video on units and numbers.